simple string wave, okay? So we're starting with this, right? So here's a stretched string. So the only parameters I need to describe this string are its length and its mass per unit length and its tension. And then I can describe like a wave, like if I go like this. See, the wave went down, the disturbance went down the string and it came back. Or I can do like a sine, right? And the sine goes down the string and comes back. This is my favorite demo because when you're looking from here, it looks awesome. Right? And you guys are like, he's just shaking a fucking string. What's this? Like, you don't see anything. All you see is just, a string shaking around. But you should see it from here. It's really cool. Okay. Wow. Okay. But you get the idea. Like a disturbance goes down the string. So now what we want to do is see if we can describe that mathematically here. What's the word next to string? Canonical. I think that's the word I want. I don't know. The classic wave. All right. So let's see what it would take to describe it. Okay. So the string is the medium. A medium is not a body. That's what I was saying before. We aren't just going to F equals ma a particle and get this right. We're going to think of it this way. Like here's a string, and it's between two clamps. Like I was holding it over there. I tied it to this thing over here so y'all can't leave. And we want to describe it mathematically. We would say the deflection is in the y direction, but we have to keep up with everything also along the x direction. It does all these positions in space. So we're keeping up with the deflection in y versus its position in space. And also, it varies in time, right? Because it's a wave. Okay. So we have to consider deflections in y along position in x for all time t. So we have to solve this. Y is a function of x and t. That's like the function we're trying to solve for. And we're not going to do it because this isn't sophomore physics. I'm just trying to give you an idea of what we're doing here. So there's something about this that should have you, like somebody should have screamed. You guys are so expressive. There should have been oh my God. Look, there's two independent variables. Actually, you just don't even know that you should be afraid yet. That's the deal. You're afraid of something called multi. This is beyond multi. Okay, this is much worse than multi. So basically, this is a partial derivative. A partial differential equation. Oh my God. And you guys are like, yeah, I did those in 8th grade. I know, but still. Most people are afraid of them, okay? Partial differential equation. So harder to solve than regular differential equations, okay? Taking partial derivatives isn't so hard, but solving partial differential equations is hard. Because the thing on the right, the wave equation, is all crazy pants. Let's see. So we're not going to solve it. We're just going to talk about it, okay? If we were to apply F equals ma to pieces of string, we would get some special equation called the wave equation. We'd get this. d2y dx2 equals mu over t. This is the mass density. And this is the tension. d2y dt2. Right? This is the wave equation. We are not driving it. We're not going to solve it. But it can actually greatly enhance your intuition for how waves work. Okay? That's why I wrote it down. And that's why I'm going to do this demo. Okay? This is F equals ma for a string. What is d2y dx2? Let's think, if I take this string and I'm going to shake one end of it. Okay? Again, wait a minute. You could see it if I were to go like over here. This is a horrible idea. I love horrible ideas. I love it. Now you're actually going to see it for the first time. Oh my God. I'm going to catch myself on fire. It's going to be right down your alley. It's going to go over your head. I hope I'm tall enough. Yes, this will be beautiful. Now everybody gets to see the wave along the axis that I've been looking at it for all these years. It's the first time this demo hasn't sucked. Oh, I'm sorry. All right, so I'm going to shake. Oh, man. Oh, you can't see shit down there. Okay. I'm going to shake this end, and you're going to see this pulse go down. Whoa. Didn't it look cool that way? Still no? Okay. Right? If I shake my hand here, then the disturbance goes down there. I'm shaking in time here, and I'm making a disturbance in space there. Totally worth it. Okay. Let me see if I can not clothesline anyone here. Oh, this was triggering. I'm sorry. Okay, so now you saw that. So what we got to do is think about what these two things mean. And this is the curvature. Right? So your hand holds the string, and your hand moves up and down like this. And what does that do? It makes the string, the string do that. Okay? So this is d2y dx2. Right? If you were to plot y versus x, and if it's flat, it doesn't have any curvature. It has no second derivative. If it's a line, it doesn't have any curvature. It has no second derivative. It has a first derivative if it's a line. But if it's curved, it has a second derivative, and that's what that is. And if it's curved, it'll feel a force pulling it back to be straight. So that's curvature. So curvature equals if you shake it with your hand. Right? So if I shake one end with my hand, if I give it a d2y dt2, if I accelerate it, I generate curvature in the string. Okay? How fast does that curvature move away? The speed of the wave. Right? If I make a sinusoid with my hand, shake it at the sinusoid flies away at some speed, and that's here. The speed is not equal to that, but the speed is related to that. Square root of t over mu. So that's 1 over v squared right there. Right? So all the wave equation says is if you shake one end of the string, it creates curvature in the string, and it runs away at 1 over v squared, or square root of t over mu. Right? So there's your intuition. Without having to do all the work, you get all the intuition. Well,